Salutations, countrymen and non-countrymen from wherever you're watching, I don't really mind. Welcome to another video. This time it's paper 2 from 7th of June 2023, made by Edexcel for higher tier maths. So we've done paper 1, now it's paper 2, so you can use a calculating device often called a calculator, which is its street name. So let's have a look together at question number 1, and sometimes I'll talk you through more than one method. So calculators to hand, let's get going. Question 1, we have to work out the value of 25 minus this square root all over 6 plus 2 plus 1, 2.1 squared rather, writing down all the figures on your calculator display. So get your calculator ready, and as long as it's a good calculator, just type it in exactly as it looks essentially. So what I've got here, I've got a fraction, so type the fraction line. Now I'm going to do 25 on top minus tick 43.87 all over 6 plus 2.1 squared. My decimal looks like a comma, don't worry about that, that's a European version. So if I press equals now, I get 1.76527.923. So 1.765 and the rest of it 27923. Just double check I got that right. I'm pretty sure I have. I don't want to have miscopied a number. 765 27923. Bingo. It then says to work out the value of the reciprocal of 0.625. So the reciprocal of a number just means 1 divided by itself. So that just means or just means 0.625 to the power minus 1. One and the same thing. So there is actually a reciprocal button on your calculator, which I'll show you now. It's just a button which says to the power minus 1. So on here, on my calculator in fact, I've got it so that it's can't see it. Maybe I'm wrong. I'm sure calculators used to have it. Anyway, never mind. Essentially, we're just going to do 1 divided by 0.625. And we get 8/5, or 1.6 if you want to. So 1.6 or 8/5. Question 2, we have to write 60 as a product of its prime factors. I'm going to show you the foolish way of doing this. Do it manually. So, can we divide 60 by any number apart from 1? Yes, we can. We can divide by 2, which gives 30. So, if we see a prime number, we circle it and stop. So 2 is prime, so I'll leave that 1. 30 isn't, so I'm going to go again. 30 I can divide by 2, which gives 15. 2 is prime, so I'm going to circle it and colour in. 15 isn't, because 15 I can divide by 3, which gives me 5. Now because 3 is prime and 5 is prime, I've got prime numbers at the dead ends everywhere, so I'm done. So therefore, 60 equals 2 times 2, I'm going to call that 2 squared, that's a better way of writing it, multiplied by 3, multiplied by 5. Product means written next to each other and multiplied together. So why does it say that's a slow way of doing it? Well, it sort of is. You can save yourself a few precious seconds. Each second's worth saving, I'm not being sarcastic for once, by doing this on a calculator. So if you type in the number you want to find the prime factorisation of, in this case 60, type a number in, press equals, and then if you press shift and then fact, it tells you it nicely. 2 squared multiplied by 3 multiplied by 5. No pain whatsoever, and slightly quicker, so you can save yourself precious time on an exam by knowing your calculator very well indeed. Question 3, we're talking about 48 counters which are in a bag. There's only red and blue counters in the bag though, and the number of red counters to the number of blue is a ratio of 1 to 2. Helen's got to work out how many red counters are in the bag. She reckons, or she says, there are 24 red counters in the bag because 1 is half of 2 and 24 is half of 8. Is Helen correct? You must give a reason for your answer. Well, she's misunderstood a ratio. If the number of red is 1 and the number of blue is 2, that means 1 part red, 2 parts blue, 1 plus 2 is 3. So actually what she needed to do would be to do 48 divided by 3 rather than halving it. There's a few different ways you could write the answer to this in terms of what she's done wrong. I'd probably just say something along these lines. Helen is not correct because 1 plus 2 is 3 parts, so the number of red counters is 1/3 of 48, which is 16, not 1/2 of 48. If it's a mistake that's been made by someone in a question and you're saying, are they correct or not, give a reason, a solid strategy is just to correct them yourself and say what the correct answer should be. Question 4. N is an integer and n is in between -2 and 5. So this symbol here means n is allowed to be -2, but this symbol here means n has to be strictly less than 5. And n is an integer means n is a whole number which is allowed to be negative. So of all things n can be, it can be all of these numbers here. It could be as low as -2, -1, 0, 1, 2, 3, all the way up to 4, but not 5. We want the greatest possible value of this one, which clearly is 4. So we're not interested in any other value apart from the highest one, so therefore n equals 4. For part B, on the number line below, show the inequality -4 to m to 1. Importantly here, have a look at the values either side of the variable. I've got -4 on one side and 1 on the other. So these values here, I'm going to put circles above them on the number line. So -4 and 1, 2 circles here and here, and a line joining them. Finally, the only thing to consider is if a circle's hollow or filled in. This circle's filled in because of this symbol here. Because m is allowed to be equal to -4, I colour this in, which represents m is allowed to be inside the circle. Because m has to be less than 1, m isn't allowed on the inside here, so that's left blank and hollow. Another way I think about it is this symbol here takes more ink because of that extra line underneath. In the same way, it'll take more ink from your pen to fill in the dot rather than leaving it hollow. Part C is an inequality to solve. Solve 2/5 g minus 4 needs to be less than 6. We solve this in exactly the same way as you would do any equation. So I want to isolate g, get it on its own. So first of all, I'm going to add 4 to both sides. That will then give me 2/5 of a g is less than 6 plus 4, which is 10. Now, I don't want 2/5 of g, I want to have g on its own. G's been divided by 5. So what I could do here, I could undo dividing by 5 by multiplying both sides of this by 5. So 2/5 times 5 is just 2. So on this side, I'm going to get 2g is less than 10 times 5, which is 50. Finally, if I now divide both sides by 2, I can see that g must therefore be less than 25. Question 5, we have a triangle and a rectangle. All measurements are in centimetres. The area of this triangle is 10 centimetres greater than the area of the rectangle. So this is a lot of information actually in one sentence. So just section it out step by step. Area of a triangle, 10 centimetres greater than the area of a rectangle. Well, we can put this into an equation like so, because the area of a triangle is half times base times height. So half times 8 times 6x, that's the area of a triangle. 10 centimetres greater just means plus an extra 10. That means 10 more. So 10 centimetres greater just means plus an extra 10. And the area of a rectangle is also just base 5 multiplied by its width or height, which is 4x minus 1. So putting this from words into an equation, we're saying the area of this triangle is 10 centimetres more than the area of the rectangle. So now all we need to do is to simplify and solve. Half times 8 is 4, half of 8 is 4, 4 times 6x is 24x's. Expand these brackets, 5 times 4x is 20x, 5 times minus 1 is minus 5, and of course a plus 10. If I now take 20x's from both sides, to get all the x's together on one side of the equation, 24x minus 20x leaves me with 4x's. No x's will remain over here, but I will have minus 5 plus 10, which overall is 5. Then if I now divide by 4, on both sides, I can now see that therefore x must be 5/4 or equal to 1.25, as so. Question 6. Last year a family recycled 800 kilograms of household waste, and 50% of this waste was paper and glass. We're also told the weight of paper recycled to the weight of glass recycled is in this ratio 12:7. Calculate the weight of glass for family recycled. So they recycled in total 800 kilograms of household waste, and 50% of that 800 kilograms was paper and glass. So what I can do now is work out what 50% of 800 was, and that will tell us the mass of recycled paper and glass this family have got through. 456. So they must have recycled 456 kilograms of paper and glass. As well as that, the paper recycled to the glass recycled in the ratio 12:7. And so I can now split this 456 into this ratio 12:7. So 12 lots of paper, 7 lots of glass. Obviously that gives a total of 19 lots. But the total amount recycled was 57% of that 800 kilograms, which is 456. So how do I go from 19 and scale that up to 456? Well, if I were to do 456 divided by 19, I get 24. And that tells us that this final row here needs to be 24 times bigger than the first row. So in other words, my multiplication factor is 24. So if I multiply all these values by 24, I'll arrive at the correct values of paper and glass recycled. So 12 times 24 and 7 times 24. 12 times 24 is 288. And 7 times 24, that will give 168. Now, we're only interested in the weight of glass this family recycled, so the answer we're only interested in is just for 168 kilograms of glass. So our final solution is 168 kilograms of glass. Question 7, a number D is rounded to 1 decimal place. The answer is 12.7. Complete the area interval for D. So if it's been rounded to 1 decimal place, I always sort of imagine this as the times table you're looking at. Imagine the 1 decimal place times table. 0.1, 0.2, 0.3, 0.4, 0.5, and so on until you get close to 12s. So imagine the 0.1 times table in the region of 12.7. So going up in 0.1s, eventually get to 12.5, 0.6, 0.7, 0.8, 0.9. But if it's been rounded and it's closer to 12.7, that must mean the value it was before it was rounded off must be nearer to 12.7 than either 12.6 and 12.8. So if I just consider the halfway points in between 12.6 and 12.7, and again halfway between 12.7 and 12.8, D must be in between these boundaries here. That's where D must be. Now, if it were 12.65, that's allowed because 12.65 would round up, hence the thick line, it's allowed to be 12.65. However, if it were exactly 12.75 in the absolute limit, that would have made it round up to 12.8. So 12.75 is the upper bound, which it strictly isn't actually allowed to be. So our completed area interval is 12.65 inclusive, all the way to 12.75 exclusive. And that's our answer. Question 8 is about compound interest. So Tamsin's buying a house with a value of 150 grand. Her house increases by 4% each year. Whereas Rachel buys hers for 160 grand, and the value of her house increases by 1.5% each year. At the end of 2 years, whose house has greater value? You must show how you get your answer. So let's just think about Tamsin's house and Rachel's house separately, in red and blue boxes. So for Tamsin, she buys it for 150,000. But her house increases by 4% each year. So before anything happens to a value, it always starts off as 100% of its original self. So 100% plus 4%, it will become 104% of its original self, and as a decimal, 104% is 1.04. And that has a particular significance. This is what's often known in textbooks and by myself as the decimal multiplier. This is the decimal we're going to multiply the initial value by the number of times the house is increasing in value. It increases in value each year, and here we're talking about 2 years. So what we're going to do here to work out Tamsin House's final value is do 150,000 multiplied by 1.04 squared, because it's 2 years. So 150,000 times 1.04 squared, that'll give 162,240. We use a similar approach now for Rachel's house. So her house is going up by 1.5% each year. So now 100% plus 1.5% would be 101.5%. Dividing by 100 will tell us the decimal multiplier. This one's going to be 1.015. So for Rachel's house, the final value will be 160,000 multiplied by this squared. If you try that on your calculator, you should find you get 164,836. The question's asking us for whose house has a greater value, which house is more valuable. Rachel's house is worth more than Tamsin's, therefore Rachel's house is our answer. Rachel's house has a greater value. Question 9, we've got a cumulative frequency table. Information about the ages of 80 people working for a company. On the grid opposite, draw a cumulative frequency graph for the information. Now, for cumulative frequency, we need to always remember to plot from the endpoints. Endpoints always. So, just a point there, do plot from the endpoints. So the 20s here, just ignore those. We're going to start plotting from 30, 40, 50, 60, 70. So the first one, like coordinates, we're going to go along to 30 and up to 20. So that's the first point here. The next one, 40 along and 48 up, will be here. And then 50, 64 will be this point here. Then 60, 60 and 75 will be over here. And then finally, at 70 and 80 will be all the way at the top, this dot here. Then what you need to try to do is do a smooth curve going through each point, not skipping any point. It's not a line of best fit, it needs to go through every single point, ideally with a smooth curve, something a bit like this. And that's now done. So you need to join your points with a smooth curve. Examiners will often allow a straight line in between points if you really struggle terribly to do a curve. For part B, we're now going to use this graph to find an estimate for the median age. Median means the middle age. So if there's 80 people, imagine stood in a row from youngest to oldest, the person in the middle would be about the 40th. So I'm looking for an estimate of how old the 40th person is. So I'm going to read off my graph at 40 and then go down to find that age. So if I do that, go along to 40 and then go down, for my one at least, I get an age of 37 years. Depending on how you've done your curve, you should hopefully get somewhere in between 36 and 38. So plus or minus a year from 37, you should have that accurately enough. Question 10, we have a biased dice. Important, it's biased. Can highlight that straight away. The table shows information about the number that the dice lands on each time. So as you can see, it doesn't land on 1, 2, 3, 4, 5, 6 evenly, not even close. An unbiased dice, you wouldn't have an even number necessarily. But if you look here, we've got like more than double the number of 6s than have a number of 2s. So this dice is not normal. I can't just assume the probabilities for getting a number is 1/6. This is a clue. I can't just use standard probability. I need to use relative frequencies. We can't assume all probabilities are the same because of this snippet of information here. So what do we mean by relative frequency? All that means is, as a proportion of the total number of rolls, what number came up? So, for example, there are 60 rolls. If I got the number 1 12 times, the relative frequency of the 1 would be 12 out of 60. If I got the number 2 7 times out of 60, that relative frequency is 7 out of 60, and so on. So I could just actually do this as a table of relative frequencies. This one would be 12 out of 60, 7 out of 60, 8 out of 60, 9 out of 60, another 9 out of 60, and finally 15 out of 60, which I suppose if you wanted to, can simplify down to a quarter. Work out an estimate for part A for the probability that the dice will land on a 6 both times. She's going to throw it twice. What about landing on a 6 just once? Well, 15 times out of 60 it landed on a 6. Now that's a quarter. So that tells us for just like one roll, obviously we're going to land on a 6 for just one time. That means the chance of rolling a 6 is going to be, best guess, is a quarter. 15 out of 60 goes to a quarter. Therefore, if she rolls it twice, and we want an estimate for the probability of landing on a 6 both times, we want a 6 first and a 6 again. So what we need here is a 6 and then another 6. So if it's one 6 and then another, I take 1 quarter and then multiply by another quarter. So this probability is going to be a quarter multiplied by a quarter, which is 1/16. Sally's now going to throw the same dice n times and record the number it lands on each time. She will use her results to work out a more reliable estimate for the probability in part A. So what can you say about the value of n? Well, if she's going to do an experiment, it's going to be more reliable. The more reliable an experiment is when the number of trials is increased. So if her results must be more reliable, she'll need to roll it more than 60 times. So what we can say about the value of n, to put it as simple as I possibly can, n needs to be more than 60. N needs to be bigger than 60. The bigger, the better. The bigger it is, the more reliable her data shall be. Question 11, I need to solve these simultaneous equations. 2x plus 6y equals 5, 3x minus 4y equals minus 12. These are both linear. The standard method is to get either the x numbers the same or the y numbers the same. So we can do any way we want to be honest. So method A, I'm going to show you how you could do it by getting the same x coefficients. Method B, I'll show you how you could do it if you want to get the y values to match. So first we'll ignore the signs. Just look at the numbers in front of x, 2 and 3. They don't match. How can I make them match? What's the lowest common multiple of 2 and 3? It's 6. So the key here is to spot that if I multiply the top one by 3 and the bottom equation by 2, I'll get both equations 6x in each. So if I do that first, multiply the top by 3, the bottom by 2, the top one becomes 6x plus 18y equals 15, and doubling everything on the bottom gives me 6x minus 8y equals minus 24. So now I've got matching numbers of x's, a positive 6 and a positive 6 below. Now, looking at these numbers, we now consider the signs of them. If the signs are the same numbers of the same 2, we subtract one equation from the other. So because both these 6's are both positive 6's, we subtract one from the other. So because of that, subtract 6x takes 6x cancels, 18y minus 8y becomes plus 8y, so I get 26y there, and 15 minus 24 gives 39. So to find y, I can just divide 39 by 26 now. So y will be 39 over 26, that simplifies to 3 over 2, or 1.5. Now I know that y is 1.5 or 3 over 2, I can now plug this back into one of the initial equations to generate a value for x. So if I now put this back into the top equation, 2x plus 6y equals 5, but replace y with 3 over 2, like so, then the next step, if I just take 6 and times by 3 over 2, that gives 9. So 2x plus 9 equals 5. Subtract 9 from both sides, gives me 2x is minus 4, then dividing by 2, x would have to be negative 2. So x is negative 2 and y is 3 over 2. What if we did it the other way? What if you wanted to get the y values the same? If I just copy down the same initial equation again over here, that's the final solution to that one, sorry. So this one, if I just copy down the same equations, to get the y values matching, I could get them both to become 12y's. I could double everything on the top to get 12y, and triple everything on the bottom to get minus 12y. So the top equation will become 4x plus 12y equals 10. The bottom becomes 9x minus 12y equals minus 36. Now, looking at the signs in front of my same numbers. My same numbers are 12s. One is a plus though, and the sign in front of the other same number is a minus. These signs are different, and the signs are different, we add the equations together. So, 4x plus 9x will give 13x's. 12y plus minus 12y, that'll cancel. and 10 plus minus 36 will give minus 26 overall. So I get 13x equals minus 26. So I can now divide both sides by 13, so x will be minus 26 divided by 13, which is minus 2. That's annoying, that should be a minus there. So now I can plug in the value of x being minus 2 into one of these starting equations. I'm picking this top one here, 2x plus 6y equals 5. So replacing x with minus 2, this now becomes 2 times minus 2 plus 6y equals 5. 2 times minus 2 is minus 4, so now I get minus 4 plus 6y equals 5. If I now add 4 to both sides, I get 6y equals 9. Then finally dividing by 6, y must be 9 divided by 6, which simplifies to 3 over 2. So therefore, I've got x being negative 2 and y being 3 over 2. So that's my complete solution, which you'll spot is exactly the same as what I had here. So no matter which round you go, the answer to these is x equals minus 2 and y equals 3 over 2. Question 12, we've got different points on a circle, centre of the origin. AB is 8 centimetres and BC is 10. So let's just label these on first of all. Now, I want to work out the circumference of the circle and to give you the answer to correct to 3 significant figures. So to work out the circumference is pi multiplied the diameter. So I could do with working out either the radius or the diameter. If I notice that if I go from A to C, do a line through here, that actually tells me the diameter because it goes from one end of a circle to the other, going through the radius. So I've labelled that C as in a squared plus b squared equals c squared. I can use Pythagoras, is what I'm trying to say, to work out the length of this green circumference. So a squared plus b squared equals c squared. That gives us 8 squared plus 10 squared equals c squared. So 8 squared plus 10 squared, that gives 64 plus 100. So c squared is 164. So c is going to be the square root of 164, which is 12.806, and so on and so on. And that's the diameter. Now don't get the formulas mixed up. Circumference is pi times diameter. Area is pi r squared. So to work out the circumference, I now take pi and multiply it by this diameter, 12.806. So the circumference now is this value multiplied by pi, which gives approximately 40.232. So then working this one out, as I say, rounding off, we get 40.2, correct to 3 significant figures. 1, 2, 3 sig figs. Question 13, ABC is a triangle, and we have to calculate the size of angle BAC. So for this one, BAC is the angle at A here. And I need to work out that angle correct to 1 decimal place. A key spot is I know an angle and an opposite side. So this is going to be a sine rule question. I don't know this angle here yet though, but if we worked out that one, I can then work out BAC after. So I know 70 and 18. If I now think about this one and this one as a pairing, 15 and the angle at C, I can now introduce the sine rule. This is the sine rule. Sine A over little a equals sine B over little b equals sine C over little c, where the big letters are the angles and the little letters are the sides opposite to those same angles. So using that, sine 70 divided by 18 must be the same as sine of BCA, this one here, divided by 15. So if I multiply both bits of this now by 15, I can see that sine of BCA must be 15 sine 70, all divided by 18. So therefore angle BCA will be sine minus 1 of all of that, 15 sine 70 all over 18. So if we calculate this now, shift sine minus 1, 15 sine 70, all over 18. I get 51.543. Now, I don't really want that angle, I want BAC. So therefore, angle BAC, which is the yellow one, will just be 180 minus the other two angles. So it's going to be 180 minus 70, that one, minus 1 just worked out, 51.543. So if I do 180 minus 70 minus my answer, I get to 1 decimal place, because the question's asked me for 1 decimal place, I get 58.5, because that 4 is next to a 5, so the 4 will round up to a 5. So it's 58.5 degrees. For question 14, we have to show that this algebraic fraction, x squared minus x minus 6, all over 2x squared minus 5x minus 3, can be written in the form ax plus b all over cx plus d, where a, b, c and d are all integers. In other words, a, b, c and d have to be whole numbers, but they are allowed to be negative. If you've got a question like this, where it's simplifying an algebraic fraction, it almost always is a good bet to factorize both numerator and denominator. So what I'm going to do here, I'm going to factorize x squared minus x minus 6 and also factorize 2x squared minus 5x minus 3. So I'm going to do this separately. So x squared minus x minus 6, this is a relatively standard one. We need to find two numbers that multiply to give minus 6, but when I add them together, I get negative 1. So those two numbers, with a bit of thinking, hopefully you'll get a positive 2 and a negative 3. Because 2 times negative 3 is minus 6, and 2 plus minus 3 is minus 1, as in the minus 1x. So in any order in my brackets, I need a positive 2 and a negative 3. And so the numerator factorizes to this. Now, I'm not going to make any apologies in this weird way I factorize the denominator. If you've not seen any of my videos before, you'll think this method might be a bit bizarre, but I swear down, with practice, it's the quickest method as long as you don't make the fatal mistake I'm going to mention in a second. So, to factorize something like this, the way I do it, which might be a bit peculiar, multiply the 2 by the minus 3, so multiply the a by the c, the n numbers, then forget for a second that 2 ever existed. So then we write it as x squared minus 5x, and then minus 3 times 2 is minus 6. Then factorize this one as normal. So this time I need two numbers that multiply to give negative 6. When I add them together, I get minus 5. And so again, those numbers, with a bit of thinking, you should hopefully get x plus 1 and x minus 6. The key thing with this strange method is to remember to put this 2 back in to our expression, and we put it back in by dividing the constants, the numbers in the brackets, by this number. So we just write 1 over 2, write 6 over 2. And then, if this fraction will simplify, do so, and if it doesn't, any remaining denominator, just shove in front of the x in the same bracket. So 1.5 doesn't simplify, so I'm going to put that 2 in front of the x. So I then get 2x plus 1, whereas 6 over 2 does simplify to exactly 3. So if I just replace that to x minus 3, that's it fully factorized. So what I can do here is just essentially simplify this fraction now. So x squared minus x minus 6 all over 2x squared minus 5x minus 3 is going to be one and the same thing as x plus 2, x minus 3 as the numerator, because we just factorized that numerator to arrive at this expression. And in the same way, the denominator here, you should hopefully get, using whatever method you use to factorize, you should hopefully be able to convince yourself this one goes to 2x plus 1, x minus 3. Now what I can do, because if you notice here, I've got a common fraction, sorry, a common factor on the numerator and denominator. I've got x minus 3 common to both. I can simply divide both numerator and denominator by x minus 3. In casual language, I call that cancelling x minus 3 on the top and the bottom. And so what's left then is just simply the x plus 2 on the top as the numerator, and underneath I'll have 2x plus 1. And that therefore is our final answer. Therefore, let's have a look at numero 15. Question 15, we have the first 4 terms of a quadratic sequence. We have to find an expression in terms of n for the nth term of a sequence. Importantly, it's quadratic and it has said so. This means the gaps between these numbers aren't going up uniformly, but the gaps of these gaps are. So if you have a look at the gaps of these numbers, first of all, the difference in between 3 and 9, between 9 and 17 and 27. So between 3 and 9, we've gone up by 6. From 9 and 17, that's a gap of 8. And from 17 to 27, it's gone up by 10. As you can see, the gaps are increasing. But if we think about the gaps of the gaps next, difference of 6 to a difference of 8, difference from 6 to 8, the difference is 2. And same from 8 to 10, the difference is 2. Now what we need to do is we halve the gap of the gaps. We halve this value here. We halve the plus 2. We divide it to get 1. And the answer we get once we divide the gap of the gaps by 2 is the coefficient of n squared. So 2 divided by 2 is 1. Therefore, the quadratic piece of this quadratic sequence is just going to be 1n squared, because the 2 divided by 2 gives 1. So that's our quadratic piece. Now what we need to find is the linear piece to the quadratic sequence. A quadratic you can think of as being a quadratic part and a non-quadratic part hidden inside it. So let's just remind ourselves of the sequence here. I'll just copy these numbers up and put them over here again. 3, 9, 17, 27. So Tn just means the nth term, and n is above. So when n is 1, the nth term is 3. When n is 2, the nth term is 9, and so on. So we're just actually interested, of course, in the numbers in our sequence, 3, 9, 17, and 27. So I'm going to highlight these now. Now what we do to find the linear part is we need to subtract away the quadratic part from the sequence, and what will be left will just be the linear part, an nth term like you'd see in year 7 or 8. So what I'm going to do now, I'm going to take away one lot of n squared from each of these nth terms. So first of all, when n is 1, 1 times n squared will be 1 times 1 squared, which is 1. So from this first one, we're going to take away 1, just minus 1 squared. So 3 minus 1 squared means 3 minus 1, which is 2. When n is 2, I need to take away one lot of 2 squared. So 2 squared is 4, so 9 take away 4 is 5. The third term, when n is 3, I need to take away one lot of 3 squared. One lot of 3 squared is 9. 17 take 9 is 8. And in the same way, when n is 4, I subtract 4 squared from 27. 27 take away 4 squared is 27 take away 16, which gives 11. You can now hopefully see here that this sequence is linear and the gaps are uniform. Each next number is 3 bigger than the last one, so that means it's going up in 3s, like the 3 times table. So the sequence is going to be similar to the sequence 3n. However, the first number of the sequence 2 is 1 lower than 3. So this sequence in blue would be 3n minus 1. It's going up in 3s, but it starts off 1 lower than the 3 times table. So this bit here, the linear part, is 3n minus 1. To get our final expression for the quadratic sequence, I just simply piece together the quadratic part here and the linear part here. So if I just glue these together now, I'll have overall 1n squared and 3n minus 1. And of course, if it's just 1n squared, I don't need to include that 1. I'll just put it there to emphasize the fact that it's just 2 divided by 2, which is 1. So our nth term is going to be n squared plus 3n minus 1. Question 16 is about histogram. We've got information about the number of hours some students used their phones last week. The histogram is incomplete, however. So, what we're told here is 28 students use their phone for between 30 and 40 hours. So between 30 and 40, we know information about this bar. But also as well, 24 students used their phones for between 40 and 60. Between 40 and 60 is here, so this is the bit we're missing, that what needs to be filled in for part A. It's a histogram, So already I'm feeling very, very hungry just thinking about this histogram. I can't help but think about chicken wings. Here's a portion I made earlier. I look at these and I just think, oh wow. Oh wow, they look really beautiful. In other words, why are they so beautiful? Why do fat dads want to eat them? Well, put simply, it's because fat dads feast on chicken wings. It's a scientific fact. Without being too silly about it, frequency density equals frequency divided by class width. Fat dads feast on chicken wings. This is my stupid way of remembering it, but it's so stupid it actually works for me rather well. This is our formula triangle to calculate the frequency density, essentially. So now we know, or now hopefully reminded ourselves what we need to do, we can use this formula triangle to calculate the missing bits of information. So let's return to the information we've been told. So we're told 28 students use their phones between 30 and 40 hours. So for this one, we're told the frequency, the number of students is 28, and the class width in between 30 and 40, that's a gap of 10. So I can calculate the frequency density of this by simply doing the frequency divided by the class width. So if I were to do 28 divided by 10, put my hand back there, 28 divided by 10, that gives me 2.8. So what that means is the bar in between 30 and 40 is 2.8 high. So therefore here, that gives a frequency density of 2.8. So I can now work out my scale. This height must represent a density of 2.8. So if I add this on now, I can now deduce that each big square must be 1 unit. That's 1 frequency density. This is 2, 3, and 4. So just finishing off the scale on the y-axis, 1, 2, 3, and 4, we can now use this to work out the height of the missing bar. And the missing bar, it says here that 24 students used their phones for between 40 and 60 hours. Now for this bar, the frequency, the number of students is 24, and the class width, the gap in between 40 and 60 is 20. So what we need to do here is 24 divided by 20. And if we were to try that, 24 divided by 20, you should see that gives you either 6/5 or 1.2, either or. So 1.2. And so this bar between 40 and 60 needs to be this high. So if I just add this in now, that's our final bar, and therefore the frequency, the histogram's been completed. Now part B, it says no student used their phone for more than 60 hours. This is just a way of just confirming that this bar is our final one. There's no need for any other bars beyond 60 because no student used their phone for that long. Mind you, these days, kids these days, I don't know. That's a terrible joke, I'm sorry. So now we need to work out the number of students. Now, the number of students, that means now we're interested in the frequency. So if I use this here, the frequency is FD times CW. To work out the frequency, it's the frequency density of each bar multiplied by the width of that particular bar. So if I look at this first one here, this bar is 1.6 high on the frequency density scale, and it's 20 wide. So this first bar, 1.6 times 20, that gives a frequency of 32. This bar here, the frequency density is 3.6, its width is 10, so 3.6 times 10, this bar represents 36 students. For this bar, its frequency density is 2.8 and its width is again 10. 2.8 multiplied by 10 is 28. So that bar represents 28 students. And finally this one, well, we were told that's 24, but if you want to just use the calculation, you can do. 1.2 times 20 would give you 24 anyway. So the total number of students is 32 plus 36 plus 28 plus 24, which gives you exactly 120 students. Question 17, we have to show that the equation x to the power 4 minus x squared minus 5 equals 0 can be written in the form x is the fourth root of x squared plus 5. So these questions with iterations, often the part A is very simple and formulaic. We rearrange to get x to the power 4 on its own and then fourth root it. So what I'm going to suggest we do here is we can add x squared to both sides of this equation. Or we could add 5 first, doesn't really matter. So we get x to the 4 minus 5 equals x squared. If I now add 5 to both sides, that'll give me x to the power 4 all on its own, which is actually what I want to happen. So I have x to the power 4 equals x squared plus 5. Then to get from x to the power 4 down to just x, I can take the fourth root of it. So if I do that to both sides, I can say that therefore x must be x squared plus 5, all of that cube, sorry, not cube rooted, fourth rooted, I mean to say. Now for part B, starting with x0 equals 1.5, we're going to use this formula, xn plus 1 is the fourth root of x subscript n squared plus 5. We're going to use this formula 3 times to find an estimate for a solution of x to the power 4 minus x squared minus 5 equals 0. So we're given what the first value is we're going to use. So xn plus 1 just means the next one along after xn, which is the one before it. So I'm going to show you the slower way and then the quicker way of doing this. So the slow way, just doing it purely manually on the calculator, what we can do is just type in exactly as we need. So if I make this bigger so we can see. So to get the fourth root, I'm going to press Shift, this button here, type in 4. And now xn, x1 first of all, is going to be the fourth root of x0 squared plus 5. So I'm going to type in x0, square it, and then add 5. That gives 1.640909017. So the first bit, we get this. Now for x2, I now need to work out the previous value. So x2 will be x1 squared plus 5. And so what I can do now is actually type in this number into the calculator in place of 1.5 squared. I'll show you the quicker way after. So what I'm actually saying here, ironically I'm doing it, but I'm telling you not to, because just wait for the quicker method. This is probably not what to do because it is a quick way of doing it. So again, I need to make sure I've typed in all the numbers correctly and not mispressed. But the second one should be 1.6653980002, like so. Now the final one, x subscript 3, will be the square root, whoops, that's meant to say x1 squared, I do apologise. That should say x subscript 1. So the next one, we just use this value here. So if I go back on the calculator and type in this now, instead of 1.64 and all that, 1.6653980002. So press equals, we get 1.6697 and so on and so on. So this one, x subscript 3, the very last one, is this value here. And again, annoyingly, I've forgotten to correct that little subscript. I should say x subscript 2. And that's the final answer because we've done it 3 times like the formulas, like the question, sorry, has asked me to. I did say there's a quick way of doing this, so I'm going to just quickly show you now. So the start step is exactly the same. We just type in the fourth root of 1.5 squared, using that for 1.5, plus 5. Press equals. That's your first time. Now the second time, if I just toggle back, delete this 1.5, and then just type in A and S, my calculator stored my previous x value. So my calculator stored x1. So now I can just type that in. Press equals. That's x2. And now, because it's already saying A and S squared, my calculator will then use a previous version to generate the next answer. So I just press equals again, without even pressing anything else, but just the equals again. I then get the third value, which is my final one, what I need, 1.6697630088. So the A and S function of the calculator does pay dividends, saves time and effort, and makes you very much less likely to make a mispress when typing in a long, weird decimal value. So that's the final answer in green. You can round it slightly if you want to, but if in doubt, just write down fully what your calculator says. Question 18. This is a stinker of a question. The way I'm going to show you how to do it is just something I've sort of intuited. There are other ways of doing it. I'm going to give you the slickest method. So first of all, I'm told that 2a to 5c is in the ratio of 6 to 25, and the ratio of 4b to 7c is in the ratio 20 to 21. I need to show that the ratio of a plus b dot dot b plus c is one and the same as 17 to 20. So if I just section off these bits of information, one in blue and one in green, let's start with 2a to 5c is the same as 6 to 25. I'm going to colour code A as yellow, B can be blue, and C can be green. So the first bit, I've got that the ratio of 2a to 5c must be 6 to 25. Going back to basics, if I just consider what 2a means, it means 2 multiplied by a, and 5c means 5 multiplied by c. So if I just write this explicitly, I've got this. So now, I'm just thinking, I wonder if I can get these to match. 2 times a needs to match up to 6, and 5 times c needs to match up to 5. Well, couldn't that be the case if I had 2 times 3? Because that would give me 6. And if c were 5, 5 times 5 would be 25. So using this line here, what I can next say is 2 times 3 to the ratio of 5 times 5 would indeed be 6 to 25. So therefore, from this we can sort of see the ratio of a to c is required to be 3 to 5. So from this bit, we've got a ratio of a to c. We can now do something similar to the ratios of b to c. So this information I've boxed off in green, I'm going to put here now. And again, if I write 4b explicitly as 4 multiplied by b, and 7c explicitly as 7 multiplied by c, I get this. And now just by considering what b would have to be to make 4 times b to be 20, and what 7 times c to get 21. So what would c have to be to make that work? Clearly, b would have to be 5, and c would have to be 3, and that would match up nicely and exactly. So therefore, in the similar way to the blue, I can see that the ratio of b to c must be 5 to 3. So now I can put these into a ratio table comparing a and b and c together. So if I just have a yellow column for a blue column for b, and a green column for the c values, I can now try and get these to match up. So a to c was 3 to 5, b to c was 5 to 3. 5 and 3 don't match, but I can make them match. What's the lowest common multiple of 5 and 3? It's 15. So if I can convert both of these values to 15, I'm on my way to getting the answer. So to go from 5 to 15, I'd have to multiply by 3. So therefore do the same with that a. So a times 3. 3 times 3 gives 9. And for the middle line, to go from 3 to 15, I would have had to have multiplied by 5. Because 3 times 5 gives 15. So in the same way, if I do this for the b on this row as well, 5 times 5 is 25. So therefore, I've got the ratio of a to b to c is 9 to 25 to 15. But the question's actually asking us the ratio of a plus b to the ratio of b plus c, which is slightly complicated. But from this, we've got all the stuff we need. So therefore, a plus b to the ratio of b plus c, because a is 9 parts and b is 25 parts, that's the same as 9 plus 25 to the ratio of b plus c. So just colour coding it. A, 9 parts. B, 25 parts. On the other side, B, 25 parts. And C, 15 parts. So just simplifying these down. 9 plus 25 is 34. 25 plus 15 is 40. And then if I just divide both sides by 2 to simplify, I've arrived at the solution I need. So half of 34 is 17, and half of 40 is 20, and that is exactly what I wanted to show. So thankfully, we've done. That's question 18 wrapped up. Question 19, ABC is a right-angled triangle. So it's talking about bounds here, correct to the nearest millimetre, blah, 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 blah. But actually, we want the lower bound for the size of the angle marked x. You must show where you're working. So before we get into bounds, we're trying to find an angle inside a right-angled triangle, and we know two sides. So it's going to relate actually to SOHCAHTOA before I can even think about anything else. We need to work out an angle marked x, which is this yellow one here. And just reminding again of what I said, SOHCAHTOA, we can now figure out which of the SOHCAH or TOA functions we need to solve this problem. So opposite to x, which we've drawn the line opposite to x, is 9.3. That literally means that's the opposite side. So I know the opposite side, so I'm going to ring in red O on any O I see in these triangles. Now I also know 12.6. This side here is the longest because it's opposite to the right angle. So I know the hypotenuse, so I'm going to ring in blue any H I see here. Now the triangle we can use to solve the question is the most highlighted one, the triangle in which we know the most information. The only triangle in which I know two sides, or can use two sides, is the SOH triangle. Therefore, it's going to be this triangle we're using, in other words, sin or sine. So these other two, cos and tan, we don't need. I'm going to just make these disappear. So now we know it's going to relate to sine, and also the fact that it's going to be bounds. We can now start thinking about these bounds. So AB is 3.9 centimetres, correct to the nearest millimetre, and AC is 12.6, correct to the nearest millimetre. I'm not going to lecture you about the mechanics of how bounds work again, but I did mention briefly in question 7. So if you want a very brief refresher, go to question 7 on this paper. That was a bounds question. But to keep it fairly brief here, if AB is 9.3 to the nearest millimetre, the lower bound will be 9.25 and the upper bound will be 9.35. So that's the bounds for the opposite. Minimum opposite 9.25, max opposite 9.35. Similarly for AC, the hypotenuse, if it's been rounded to 12.6 to the nearest millimetre, then the lower bound will be 12.55 and the upper will be 12.65. So next, remember that sine is O over h. The maximum value of sine, because sine is essentially a fraction, will be when the opposite, the top of the fraction is at its biggest, and the denominator, what you're dividing by, is its smallest possible thing. So this is what sine of the angle is, made maximum, not the angle itself. Remember, at some point we're going to need to do sine minus 1. But first of all, let's think of what sine max is. So if I input the opposite maximum, which is 9.35, and the minimum hypotenuse, that's the fraction I'm working with. And if I tried 9.35 divided by 12.55, I'd get this value here. But that's sine of the angle. That's a bound of the sine of the angle. So remembering to find the actual angle, what I need to do is sine minus 1. So I could either use this decimal, or I could just type in this fraction. So sine minus 1, 9.35 divided by 12.55. That gives me the angle size when sine is at its maximum, 48.16-ish. So that was one potential angle. Sorry, my voice went strange there. I thought I was on the verge of coughing, but I didn't. So it's tempting to think, because I want the lower bound, why have I done that? I just want to make it clear that because sine of an angle isn't the angle itself, at this stage of your understanding, it's best to just check both maximum sine and minimum sine. If you're doing a question about a cosine, it'll be more complicated. So although I can reason out to you why you just need to check one bound, try them both, exhaust all possibilities and convince yourself that you found the right one. So if I now just try the minimum bound, so sine x made minimum will be when the opposite is minimized, then the hypotenuse is maximized. So the upper bound for this one now is going to be O min divided by h max. The minimum opposite would be 9.25. Maximum hypotenuse is 12.65. There's a decimal if you want to. You could write it like this. So if I now do sine minus 1 of that to find out what the angle is when sine is minimized, if I could just toggle back and change this to a 6.5, and that becomes 2.5, I get here 46.989, and so on and so on. So I've got my two boundaries for sine maximum and sine min. Therefore, one of these angles will be a maximum angle and one of the angles will be a minimum angle. So it's quite clear to see the minimum angle is when sine of angle is minimized, which might seem common sense, but common sense can sometimes be counterintuitive to the truth. So now we need the lower bound, of course. So we've checked both bounds. This one's definitely the smaller, so therefore 46.99 degrees rounded off is therefore our lower bound, because that's a smaller angle than that one. Question 20 is about vectors. So ORT is a triangle. From O to T is vector A, and from R to T is vector B. M is a point on OR such that OM to MR equals 2/3. So from this we can make a point actually. What that means is that OM, in fact I'm going to call it, OM is basically just 2/5 of the whole length from O to R. It's just that piece of it. What we need to do is to express MT in terms of A and B. So MT is basically going from M all the way to T. So I'm after an expression for that. So how do I go from M to T? Well, what I'm thinking here is I could go M to O first, could stop off at O, then once I'm at O, I could go from O to T. So I'm just going to leave them in letter form for now, so then I can go from O to T. But, of course, M to O, I don't know any vector for M to O. All I know about M to O is it's 2/5 of the length from O to R. So I can say from O to R or from R to O. But because I'm going from M to O, I'm going to say it's 2/5 of a vector from R to O. Plus, of course, OT. So that's going to be 2/5. But from R to O, how would I go from R to O? I'm not given any vectors which tell me. Well, I can go from R to T first, and then I could go from T to O. And then, of course, plus OT. So that means it's 2/5. Now the vector from R to T, that's vector B. That's 2/5 of B plus TO. Now from T to O is along the line, the vector A, but it's going in the opposite direction. So this is going to be minus vector A. That's minus A. And of course, OT itself, from O to T, is just normal A. So I can now expand this out if I want to. So I get 2/5 B minus 2/5 A plus A. So M to T, A minus 2/5 an A, overall it gives me 3/5 of an A plus 2/5 B. So that's my final answer. Or if I want to, I could say it's 1/5. Just factorising out a fifth. You don't have to, it's just optional this. 3A plus 2B. So either of these answers is suitable as a final answer worthy of full credit to the examiner. This one or that one makes no odds. Question 21. Here's a graph of f of x. Looks like a trapezium just to the left of the origin. For part A, we need to draw the graph of y equals f of x minus 4. So it's one and the same thing, it's just that here, the whole thing is going to move 4 units down because of this minus 4. This minus 4 isn't inside the f brackets, so it affects y in a common sense way. So this thing here is going to just go 1, 2, 3, 4 down. is going to end up at this place here. So that's where the function ends up being drawn. So you need to draw it here to get the mark. For part B, we need to now draw f of minus x. So this time, the change of f of x to f of minus x is inside the brackets and is affecting x. It looks like the x has been multiplied by minus 1. Essentially, you can think of it as being divided by minus 1. This here means where x was negative, we're just switching its sign. So where x is negative, it becomes positive. If x were positive 2, for example, it becomes minus 2. So x just switches from one side of the x-axis to the other, it gets flipped. It's a reflection in the y-axis. And so this trapezium here will end up being over there next time. And so we just need to sketch in this shape, and then we're done. Question 21. Question 22, 23 and 24, we're now getting on to the real business end of the exam paper. These questions are really quite challenging. Anyway, question 22. We're told here that there's only blue and red pens in a box. The number of blue pens is 4 times the number of red pens. Okay, so this is some key information we're going to use in a second. Rita takes 1 pen at random from the box, she records the colour of the pen, and then she replaces it in the box. So that's really important, she puts the pen back. So probabilities aren't going to be changing from one pick to the next. She's going to pick this n times, where n is actually 2 or more. We need an expression in terms of n for the probability that Rita gets a blue pen at least once and a red pen at least once. This is really hard to even know where to begin. So my suggestion here would be to just think about this case by case, starting with if n were to be 2, then if n were to be 3, and see if we can spot a pattern, because maths is almost always about the patterns. So let's just consider this step by step. So blue pens are 4 times more numerous than red, so from this we can work out a ratio essentially. So from this information, we know that 80% of the pens must be blue, 20% must be red, because if you split them into ratio 4 to 1, you get 20% to 80%. So if 80% of the pens are blue, the probability of picking the blue one is 0.8, or 4/5, and the probability of being red is 0.2, alternatively, is 1/5, for just one choosing. So the chance that she gets at least one of each, well, that's certain. One, remember, is certainty. That's certainly going to happen, apart from the probability that she were to pick either all reds or all blues. So that's the only way it can't happen. The only way she doesn't get one of each is if she picks all reds or all blues. So if we subtract the probabilities away of getting all reds or all blues, what we'll be left with is the options of her getting at least one of each colour. So as I say, let's take this case by case. Imagine there's 2 picks. So let's draw a tree diagram with 2 branches. So this is the first pick, and this is the second pick. So as we can see, which routes would work so that she gets at least one of each colour? Well, blue and blue wouldn't work, nor would red and red, because that would be all the same colour. So we can put a cross on these, but the other 2 we can tick, because this route here is a blue and a red, that would work, or a red and a blue, which would work as well. So considering 2 picks, it's 1 minus this branch here, which is 0.8 times 0.8. Remember, as you go along the branches, you multiply. And this one here we don't want, so we subtract away 0.2 times 0.2, which is 0.2 squared. So for 2 picks, when n is 2, that's what we'd have. Let's add in a third pick and see if we can pitch what's going to happen. So a third pick, we can add an extra row of branches on. So 3 picks would look something like this. And again, the only way where she wouldn't get at least one of each colour is if they were all blues or if they were all reds. Any other branch in the middle is absolutely fine, because all these ones I've ticked would be at least 1 red and at least 1 blue. So essentially, 3 picks, the probability of getting at least one of each colour is 1, apart from the chance they were all blue, so minus off 0.8 times 0.8 times 0.8, so minus off 0.8 cubed. And also, I'd need to subtract off red and then red and then red again. So I'd also need to subtract away 0.2 cubed 2. So for 3 picks, our expression would be this. Crossing off those 2 leaves us with just 1 minus 0.8 cubed minus 0.2 cubed. You may see what's happening here, but just in case, let's just consider a 4th one. 4 picks would be 4 sets of branches. So for 4 picks, here's what the situation would look like. And again, by now, you're probably going to see what's going to happen. So the chance of getting at least one of each colour is any of these middle branches, of which was loads. The only way it can't happen is if they were all blues, 0.8 to the power 4, or all reds, 0.2 to the power 4. So for 4 picks, it'd be 1 minus 0.8 to the 4 minus 0.2 to the 4. So crossing off the very top and very bottom branch and ticking the others, we'd have something that looks like this is our expression. So if it's 2 picks, we're squaring, 3 picks, we're cubing, 4 picks is to the power 4. So hopefully now this is enough to see the generalization that for n picks, which is what the question's asking, the probability of getting at least one of each colour will be 1 subtract 0.8 to the power n minus 0.2 to the power n. So for n picks, that's our expression. A very nasty question, I feel. Very, very well done, if that makes sense and you were to get that. Question 23, again, is a challenge. We have 3 similar triangles, ABG at the top, ACF, which is like this one here, and ADE, which is the overall big one. ABCD and AGFE are straight lines. And also, this bit here, ABCD, is split into ratio where A to B to B to C to D is in ratio 1 to 2 to 3. So we can have this on now. So adding on this ratio here, we'd have this. So A to B is 1 lot, B to C is 2 lots, C to D is 3 lots. So let's just call 1 lot x. So if A to B were x, B to C would be 2 x's, and from C to D would be 3 x's. We need to show that the area of ABG, which is a triangle, to the area of BCFG, that's a trapezium, so don't mix up and don't mistake you think about triangles all the time, and CDEF, which is this bigger bottom trapezium, the areas of those we need to show in the ratio 1 to 8 to 27. So let's just consider this piece by piece. So consider just the top triangle, AGB, then the triangle A to C to F like so, and the overall shape here from A to D to E. Although I've not labelled these on, that would be point C, and this would be point F here. So this is length x. This would be length x plus 2x, which is length 3x, and from A all the way down to D would be x plus 2x plus 3x, which is 6x. We can then see the linear ratio for the lengths of these 3 triangles. From small to medium to large, they're in a linear ratio of 1 to 3 to 6. So if we just put this into a table for triangle ABG, ACF and ADE, the length ratios are 1 to 3 to 6. Now, if that's the case for the lengths, the area ratios will be these numbers here squared. And so the area ratio will be 1 squared to 3 squared, which is 9, to 6 squared, which is 36. So if we square all numbers on this line, we can then generate an area ratio relating all 3 triangles. So we get 1, 9, and 36. So if the areas of these triangles in this ratio, let's imagine that the area of ABG, let's just call that A. And so if the area of ABG, we call that A, then ACF would be of an area of 9A, and ADE would have an area of 36A. So just introducing A, or you could call it X or some other letter, we'd have this. So let's just start with the small triangle ABG. We want actually a ratio though of ABG, the small triangle, to a ratio of the area to the trapezium BCFG, which is this one here, to the area of trapezium CDEF. So just considering the small triangle ABG for a second, if we say that's area A, we can add this on here. But of course, because ACF comprises of basically a trapezium with ABG stacked on top of it, then this area here will be the same as this one here. Both of these yellow areas are going to be equal to A. But if the area of ACF is 9A from this ratio table, and I've got 1A already, then the area here between BCF and G, the area of BCFG, must be the extra 8A to make the total of 9A as required. So as a calculation, area of BCFG would be the area of ACF minus area AGB, which is 9A minus 1A, which is 8A. So this here is 8A, So we can have this onto the table as well. So if we now consider CDEF, which is this bottom bit here, from C to D to E to F, is the whole of the large triangle, just apart from triangle ACF on top of it. So if I were to take this blue triangle away, ACF, which is the same as this one, so this blue here is the same as all of this here, if I took this away, this would have an area equal to 9A. But of course, this overall largest triangle has an area of 36A. So if this is 9A, the remaining bit for just CDEF will be 36A minus 9A. So therefore, area CDEF will be 36A minus 9A, which gives 27A. So we can have this into our table as well. So now we've pretty much got it. We have a ratio of areas of ABG to BCFG to CDEF. But we want to show it's in a ratio 1 to 8 to 27. At the moment, we've got this in terms of actual areas. So if I just divide this through now by A, just to arrive at just purely a numerical ratio, A divided by A will be 1, 8A divided by A will give us 8, and 27A divided by A will give us 27. So as long as we divide by A and show we're doing that, we arrive at our final justified answer and pick up every single mark we can. Question 24, an absolute beast. The diagram shows 8 identical regular octagons joined to enclose a shaded shape, this shaded shape in the middle. Each octagon has sides of length little a. Find in terms of little a an expression for the area of the shaded shape in the middle. Give your answer in the form p brackets 2 plus root 2 brackets a squared, where p is an integer. You must show all your working. Most candidates in the country will have just given up and not even attempted this one. But there is a relatively easy 1 mark we should all aim to get. We're told it's a regular octagon, so that's the easy mark, and we're going to come to that in a second. Each octagon has sides of length a, so let's label the sides on here. So each one of these here, each red straight line, will have a length of a. So I'm just going to label all of these a. So this middle shape here looks like a weird star, but the way I'm seeing it here, it's like a square with like 4 spikes on either side. So if I just section off here, so it's a square in the middle plus 4 triangles sticking out from it. This is how I picture it. As ever, there's almost always more than one way to tackle a question, but this is the concept I'm going to use to tackle the question here in this particular video. As I said, it's regular octagons. This is the easy mark. If you just do this step and then forget the paper, that's okay. 1 mark's better than no marks. How do you work out the exterior angle on a regular shape? You need to remember it's 360 divided by the number of sides on that shape. An octagon has 8 sides, so therefore the exterior angle of a regular octagon would be 360 divided by the 8 sides of the octagon, which is 45 degrees. So each outside angle of the octagon is going to be 45. So for example, this one here on the outside of the octagon, outside of this one here, that would be 45. And considering this octagon here, this bit here, the outside of that octagon again, would also be 45. So that angle's 45, and as I said, the other one is as well. So if I just consider this triangle here, both sides are 45, sorry, both angles are 45, and both sides we know are A. So angles in a triangle we know add up to 180 degrees. 45 plus 45 is 90, 180 minus 90 is 90, so we can deduce this is going to be a right angle here. And as well as that, because we know 2 sides are A, and this is the hypotenuse, we can also get an expression for the length of this dotted line here, the hypotenuse of this little triangle. First of all, though, the area of a triangle is half times base times height, so that's going to be a half multiplied by A multiplied by A. The area of this triangle will be a half A squared. Now if I try and find an expression for the hypotenuse x, like I said, we can use Pythagoras. So Pythagoras says a squared plus b squared equals c squared, where a and b are the shorter sides. So Pythagoras will tell us that this side squared plus that one squared will equal that one squared. In other words, a squared plus a squared will equal x squared. A squared plus a squared, though, of course, is 2a squared. So this simplifies to 2a squared equals x squared. And then if I square root both sides, we can see that x, the length of this side, must be the square root of 2 multiplied by the square root of a squared, which is just root 2 times by a. So x is root 2a. So we can now add this information on to our diagram and begin to actually think about beginning to piece together how to solve it. We're interested in this middle shaded shape, and we've just worked out that's root 2a. So because we're only interested in this middle shape now, we can say goodbye to these octagons now. They've served their purpose. We've got enough information to work out the area of this shape. As said before, the way I'm seeing it, this shape is a big square with 4 little triangles sticking on the outside of it. So the total area is a big inner square plus top triangle, right triangle, bottom triangle, left triangle. And to work out the area of a square, obviously we need to remember the area of a square is base times height, where the base and height are the same because, of course, it's a square. So each length of a square is going to be a, and then plus root 2 of an a, plus an extra normal a there. So I've got a plus a, 2 normal a's, plus root 2a. So this length here along the top will be 2a plus root 2a. And each one of these little triangles has an area of a half a squared. So a half plus a half plus a half plus a half is 2. So all of these would be 2a squareds, like so. So an expression for the area is going to be this side of the square squared, to get the area of a square, plus 2a squared. So this is an expression for the area of the total of all this shaded shape. So I need to work out 2a plus root 2 of an a, all squared. And my favourite suggested way for doing this is to use the grid method. So let's do it like so. So we have a grid. Let's now just work out what each thing goes into each box. So doing the boxes in any order, 2a multiplied by 2a, well that would be 4a squared. In this box would be 2a multiplied by root 2 of an a. A times a is a squared, and 2 times root 2, we can just leave as 2 root 2. So this gives us 2 root 2 a squared. This box here will be exactly the same, 2 times root 2, which is 2 root 2 times a squared. And finally, inside this box, we're going to have root 2 multiplied by root 2, which is just normal 2, then a times a, which is a squared. So this box here gives us 2a squared. So piecing all this together, we're pretty much home and dry. So the area, all this squared, gives us 4a squared plus 2a squared. So I can group these two terms together like so. So I've got 6a squared. These two bits together, I can join. So I've got here 2 root 2a squared plus another 2 root 2a squared, which gives 4 root 2a squared in total. And finally just that 2a squared at the end. So now I can group together all the different bits and pieces and simplify. So that was 2a squared. The 6a squared was from these two bits here. And of course, 2 root 2a squared twice gives this. So now if I have a look at just the normal a squareds, I've got here 6 plus 2, which of course is 8a squared. And then the 4 root 2a is just this bit here, so I've only got an extra 4 root 2 a squared. So now, comparing it to the target, I want it to be something like this. And so if you have a look at the numbers here, 8 and 4, the highest common factors are 4, so I can factor out a 4 from that. And then, to get 8, I need to multiply 4 by 2, and to get 4 root 2 from 4, I need to multiply by an extra root 2. And then I can put that a squared on the outside because it's a common term in each. So, therefore, that's our solution. So, our answer is simply, the total area is 4 brackets 2 plus root 2 close brackets a squared. Not that the question asks you to explicitly say, but if you want to, you could just make a point saying, therefore, p, this coefficient here at the very front, is 4. But the question wasn't to say that p is 4, the question was to arrive at this full expression as such. So that's question 24 completed, hence the whole paper. I hope you found some of that useful. Thank you sincerely for listening to me, for even if it was just a couple of minutes of an explanation, and best of luck in your exams. Keep working hard, never give up, and I'll see you for the next video in hopefully a few days' time. Take care from me, and because I'm recording this around the festive period, have a lovely Christmas, or have a lovely day if it's just a normal day. Goodbye from me.